I will discuss two papers, two data sets. Yeah, the whole approach is quite methodological in any case. So I think it fits well in this conference. All right, so the most prominent theories currently of our brain, they assume that our brain is basically constantly making predictions of the world around us. And these predictions allow us to interact with our world effectively. Some of those theories even go so far as to say that that's the main task of our brain. So we have a predictive organ, and all it's doing is constantly having a model of the world around us and making predictions based on that model. And there is a lot of empirical evidence for this, but most empirical evidence comes from studies that only look at a single snapshot of a prediction or an indirect consequence. So, for example, studies that look at how does predictability of a stimulus influence our perception of the stimulus. And most studies use simple static stimuli, of which often the predictability is directly manipulated. Or they use sequences of stimuli and one stimulus predicts the next one, for example. But of course, in our everyday life, we go through this dynamic world and we have to continuously update our predictions based on incoming information. And that's what I'm interested in studying. So to study this, I used a representational similarity analysis approach and extended this to dynamic stimuli. But I'll first explain how RSA is typically used on EEG and MEG data, so we're all on the same page before I go on to the dynamic extension. All right, so let's say, do I have a pointer also? It's a very small pointer. Okay. Let's say we're interested in how does our brain process these stimuli, so pictures of a ballet dancer, and we want to know how specifically the body posture of this dancer is processed and represented in our brain. So first step is to compare these two stimuli and look at the dissimilarity or the distance between these two stimuli in terms of body posture. So you can simply do that by, in this case, what we did is you have this kinematic markers. So you have a 3D position of 13 markers on the ballet dancer. And based on that, you can simply create a vector and then compare, like correlate the two stimuli with each other. And then 1 minus the correlation gives you how dissimilar they are. And in this case, they're very dissimilar, as you can see. So in this matrix, they get this red value. On this scale of dissimilarity, they're very dissimilar. So the next step would be to actually look at many more stimuli. So let's say we have 14 stimuli. Then we look at the pairwise dissimilarity between each of these stimuli. And we can fill in this whole matrix. And now, as you can see, so we have 14 by 14 stimuli. And then on the diagonal, of course, they're all very similar, maximally similar, because it's just comparing the same stimulus with itself. All right, so the next step would then be to present these stimuli to a subject. It can also be an fMRI scanner, but in our case, MEG scanner or with EEG electrodes on. And now we want to know how does the brain respond to these stimuli. So we look at one time point, let's say T is 1 after the stimulus onset. And we look at all the sensors at the one value. So basically, we have a vector of values for across all the sensors in response to these two stimuli. And then again, we can just compare again the distance or the dissimilarity between the responses to these two stimuli. Again, 1 minus correlation can work. And then we have 14 stimuli. So again, we do this for all the pairwise comparisons, and we get the same representational matrix here, the small one. But because our neural signal changes over time, also this neural representation changes over time. So we get a new representational matrix for each neural time point. Then the last step in RSA is to compare the model representation with the neural representation. This can again simply be by correlating the two with each other. So correlating this with each of those, so you get a single value per time point of how similar these two are. And this would then be your RSA result, where this is not real data, but this is just to show, this is what you would expect when the stimulus comes on, it goes up, and this would then indicate that in your neural signal, you have information about the stimulus, and specifically about the feature that we are interested in here, body posture.
So your model is not a priori based on the dance moves themselves. It's also based on empirical data. A hypothetical model.
It could be also a hypothetical model. In this example, yes. Yeah. Yeah, I guess it is empirical data that we recorded and choreographed these videos and then showed those to the. But yeah, you can have many different models about these. So you can also look at a lower level visual model, like compare the pixel-wise similarity, and I'll show you later on which models we used. And then look at how different features are represented in the brain at different time points. Okay, so this is how RSA is typically used in EEG and MEG research, but typically uses static stimuli and static models. And as I said in the intro, I'm interested in dynamic stimuli. So how do we extend this to dynamic stimuli? Right, so let's say we have now belay dancing videos instead of images. And as you can imagine now, these are two videos, and the dissimilarity between the two videos is not constant over time, right? So in the beginning, they're very similar, but then somewhere halfway, they become quite dissimilar. So if again, we have 14 videos, we can compute a representational matrix for each video time point. And now we have a dynamic model RDM and a dynamic neural RDM. And then the next step would be to compute the similarity between those for each neural by model time point. And then we get this two-dimensional RSA result. And again, this is not real data, of course, looks too pretty. But this is just to show two examples of what you could expect and what it would mean. It's a bit too simplistic, I'll come back to that. But this, in principle, would mean that if you have a strong similarity, so a strong match between the neural and the model representation in this lower right diagonal triangle, sorry, that the neural representation matches most strongly an earlier model representation. So the neural representation is lagging behind the model representation. So that's what you would expect based on pure bottom-up processing. But then if we have a prediction, you would expect that there's also some representation, or maybe even the strongest representation, up above the diagonal. Okay. Then there's one more step before there's two more steps before I show some results. So this is then some real data, but just to show one more step before we look at the data. So if you look at this dynamic RSA two-dimensional plot, these individual time points are not that meaningful anymore, because to create the RDMs, you have to already look at the combination of 14 stimuli. So we can't really go back to this and say, okay, at this point in time, something interesting happened in this video X or Y, because we don't know anymore what happened exactly in which video. So we might as well just average over this time window. And because we're mainly interested in the latency between the neural and the model representation, and do we see a difference there, or a latency that is not zero. And this is basically the same data, just averaged, and then you get this latency plot. And now we're interested in the peak of this dynamic RSA plot here. And this peak on the right side of the midline would then mean that the neural representation is lagging behind the model representation. Peak on the left side would mean that we have a predictive neural representation. Right, so one more thing that is quite important in general for RSA, but also specifically for dynamic stimuli, is that I just explained that you can use a correlation to compare the model representation and the neural representation. But of course, the stimulus, you can describe it or characterize it with different models. It has different features. Also, as you already said, you can look at many different things, pixel-wise similarity, body posture. And these are all correlated with each other. And they're also correlated over time, of course, because the models are changing slower than your neural data or your sampling rate. So instead of a correlation, it's actually better to use a regression. In this case, we used principal component regression. Maybe I should use independent component regression. Well, anyway, this worked well. So we tried it with simulated data, and until we found like we were happy with what we wanted, because what we wanted was specifically to test one model. So which variance in the neural RDM is explained by one specific model and not by any of the other models. So that's what we used the regression approach for. Yeah, okay. So we tested this idea, this approach on this data set of subjects watching ballet dancing videos. We had 14 different videos, 22 subjects, and we choreographed these videos ourselves, and we had kinematic markers, and those we used to compute this body posture models. And these are just the models that we used. So we wanted to characterize the stimuli across different levels of visual processing, from low level perceptual processing until higher level, maybe conceptual representations processing. And we started with pixel-wise similarity, so just how similar are they in terms of the light, the grayscale in each of the pixels. We also looked at optical flow factors, so those capture the motion in each pixel from frame to frame. So it is motion, but it's still very low-level motion. So if the ballet dancer in one video is doing this, but in another video she's standing a bit to the left and doing this, they're going to be already quite dissimilar because we're really looking at each pixel. So that's motion, but very low-level motion. And we separated the magnitude from the direction. And then we had this body posture and body motion models. They're already a bit higher level. But what you can also do then is look at the view invariant body posture. And that's basically because if you look at the, these two, if you compare these two, they're very dissimilar in terms of view dependent body posture, but actually they are very similar, right? Because they're doing the same posture, it's just that it's rotated. So for view invariant body posture, we first rotate one to match the other, and we translate it that it's in the same location, and then compare how similar they are. And then in this example, they would be very similar. So that's the highest level representation. Right. In terms of the MEG data, we source reconstructed the MEG data. So in principle, you could do this on your sensors. So as I explained, you could just, for one time point, make a factor of all the values in the sensors, and then correlate them between two stimuli, and then one minus your correlation is your dissimilarity. And you can do the same with EEG electrodes. But in this case, we went to source space, so we source reconstructed the MEG data with a distributed source model with minimum norm estimates. So that basically gives you, in this case, 15,000 sources across the cortical surface. And then we looked at different ROIs separately. And these 6 ROIs we selected a priori because they're the visual regions and then also regions of the action observation network that we thought were going to be involved in this task specifically. And what you then do is, so I keep pointing to the computer, but you don't see that. So let's say this is your ROI, V1. After source reconstruction, there's about 500 sources inside this ROI. So instead of your sensors, you would just create a vector of these values in each of the sources. And then, do the whole analysis and then see if there's information in V1, and you can then do that separately for those ROIs. So these 6 ROIs are 6 different analyses. Okay, then there's one more step, which I always check how I'm on time to see, is it worth to go into this detail? Yes, easily. Okay, so this is a step that we figured out is quite helpful for this with dynamic stimuli, because if you do the analysis as I explained so far, then you would get something like this, what you see here. This is for pixel-wise similarity. And as you can see, it's very inhomogeneous over time here. And that's also what I explained before. So if at each time point, we're looking at a combination of 14 videos, And as you can imagine, within each video, there are certain moments where the video is more or less predictable, or it might take more or less time to process these stimuli. So this constantly changes over time across the video. And yeah, that's not something we're specifically interested in because we anyway can't look at that information anymore. And our result here also depends a lot on how these 14 videos are exactly aligned to each other. Or let's say if in one of the videos I would have started recording a bit earlier or later, then it would be differently aligned according to the other 13, and then the result would look different. So your RDMs would look different. And yeah, we're not interested in these very specific idiosyncratic effects. And ideally, we would actually have an infinite amount of videos, or we would have one long video. That's something we're also working on now with more naturalistic stimuli, with like a movie. So you could also actually have one single long trial of an hour. And then how do we actually deal with that we make the most out of, get the most out of this data, and we lose these idiosyncratic patterns? So to solve that, we did this subsampling approach. So across 1,000 iterations, so on each iteration, you basically take 3 seconds out of the 5-second video randomly, so different for each of the 14 videos. But you, of course, you keep them exactly aligned between the neural data and the model data. And then on one of these iterations with these new 3-second realigned videos, you compute the whole dynamic RSA. And you have your dynamic RSA matrix. You do that 1,000 times and then average over those 1,000 iterations. And then you get rid of all these idiosyncratic effects that we're not interested in. And we get a much more clear average of what is the latency between the neural and the model representation, what you see here. Yeah, and then as I said before, you can then, now it even makes less sense to look at the 2-dimensional plot because we really don't know anymore what happened at each time point. So we just average and we get this latency plot. And in the end, that's what we're interested in. All right, so now let's go look at some data. So for this first experiment, we just had these simple stimuli, as I explained. And we applied this approach. And then indeed, we find this clear predictive peaks, predictive representations for the motion of the ballet dancer, and both in terms of the kinematic markers, so the body motion, and also if you look at the optical flow factor direction. And okay, so that's already interesting that we see this, but then we also see this hierarchy in time scales of the prediction, such that this highest level representation, so view invariant body motion, seems to be predicted earlier in time, so it has a longer latency than this bit lower level representation, and even this one is almost at the midline, almost at the real time. And this aligns nicely with most theories of predictive processing or predictive coding that say that you have this hierarchy of prediction, and that a higher level representation would inform, or higher level prediction would inform a lower level prediction or constrain a lower level prediction. Of course, this data doesn't really show that there is actually a causal effect between these different levels. It just shows that there are different timescales. And of course, you can imagine, and actually there's a recent study that uses simple moving dots and EEG decoding, and they also find a predictive representation, or actually a real-time representation of the moving dots position, which of course shows that we can also predict if it's a much simpler stimulus. We don't need this hierarchical structure to be able to predict anything, right? If we see something simple move, we can also predict. But if we have this hierarchical structure, then probably this does allow us to make better predictions of the low-level representations. That's the idea. And this would suggest that you need a difference in timing, right? You need first the highest level representation, and then you get lowered in level of processing, you need a smaller latency, and that is what we find. So that's in line with that. Then another thing here is actually that if we look at some other representation that seem to be lagged, but it doesn't actually really say that it's pure bottom-up processing, because there's a lot of studies that also show that our post-stimulus representation is affected somehow by prediction, like the studies I mentioned in the introduction, where predictability of a stimulus determines the perception of the stimulus afterwards. So you have this expectation suppression effects that are very clear. So in this case, I think it also, in this data, you can also see that this is probably the case, because if you look at this view invariant body posture representation, seems to be real time. And if it would be only bottom-up processing, that would really not be possible, right? Because you would expect that the pixel-wise representation would come earlier, and it all takes time before you could have a representation of the view invariant body posture. So the fact that we see this representation at 0 at real time suggests that there was some prediction happening before that allows that. And that also is in line with this earlier study that I mentioned that uses a moving dot. And they also find a real time, that decoding in EEG works best on real time. And they also say, suggest you have prediction. Okay. I think I add a lot of things, and then I'll see how I'm on time to see if I have to skip over it or not. Okay, I think I have enough time. Yes. So as you can see, these peaks, they have this little bit of a pyramid shape, right? So if we look at pixel-wise here, for example, there's also some representation before the 0 line. So you could ask, is there prediction going on there as well? But actually, the shape is mainly or highly determined by the model autocorrelations. Because of course, as I said, also these stimuli are not changing as fast as our sampling rate maybe, and they're changing quite slow for certain features. So we run a bunch of simulations, also to test our approach. And in this case, we had the simulations with no random data or no noise. So the simulated data existed exactly of the model. And then we applied our approach. So we would simulate one model, let's say pixel-wise, and then test each of the other models. So with this regression approach, test one and regress out the others. And then exactly is what you get. So when you simulate pixel-wise, you get out pixel-wise and not the other models. So this was just a way also to show that our approach is actually working and not doing something weird. But then this also shows this shape here, which is caused by the model autocorrelation. And that's what we see back in the real data as well. So you can already see here for pixel-wise that this might actually be caused by the model autocorrelation and not because there's actually a spread of the representation. So we created this extra step in the analysis to look at this. So how spread are the representations, and is there any spread above and beyond what can be explained by the model autocorrelation? And to do this, we looked at, so here on the left, you see this gray line is basically a model autocorrelation or caused by the model autocorrelation. And then this black line would be real data for one ROI and one subject. And then you can align them to each other and normalize them and then look at the difference between the two. So in this case, this would suggest that there's actually more information here that cannot be explained purely by the model autocorrelation. So we call this then representational spread. And then here, these are the results. And this 0 is now not the same 0 as here, but this is now aligned to the peak in the original result. So this peak here. And then for pixel-wise, you can clearly see that there is no spread on the left and there's only spread on the right side. So anything that we saw here is purely caused or can be explained by the model autocorrelation and not, it doesn't have to be explained by a prediction or a spread of the neural representation. But on the right side, there is. So it's not like a single time point where you have a representation, but it actually lingers on or it's sustained. And you see this for most of the representations, that they're not at a single time point, and also for the predictive ones. So you see here that there's a bit of spread on the left side, which would then suggest that there's a gradual onset of the prediction rather than a single time point. But when we initially saw this, we started interpreting it like that, and we thought this is quite interesting. But I have to say there's actually a much less exciting explanation for this spread. And that's because, again, when we look at this peak, of course, we're looking at the average of all our subjects. They might have different timings. And we're looking at the average of these 14 videos, and then within the videos at all these time points. So you're really getting an average of time, stimuli, and subjects. So it could simply be that all the spread that we see here is just caused by that, and not by some sustained representation. So yeah, sorry to to make it sound cool and then break it down again, but yeah, that's how it goes sometimes. All right, so then we actually had this first data set, but then we thought, okay, we see this representation here for view and variant body. I just explained this is probably modulated by prediction. So how can we then make sure, yeah, that this is the case? And you know, we don't really have a clear control condition where we you know, manipulate the predictability of the stimuli to see what then happens to our peaks. And this is actually what we need to make sure that this is meaningful. And so that's what we did in the second experiment. So we actually created two different conditions. So we had the normal condition, then this piecewise scrambled condition. This really served for us more as a control condition to make sure that what we're finding is real and makes sense. So here we randomly scrambled these videos in pieces of between 200 and 400 milliseconds, and we randomly scrambled them and then showed those to the subject with the idea that, of course, they won't be able to predict very far in advance. So with this, our idea was that we would basically destroy the predictability of the stimuli. But then we also thought, okay, we have this hierarchical prediction for different features, right? What happens, what happens if we reduce the predictability by reducing the familiarity that subjects have with the stimuli at one level, at the highest level in this case, but keeping the stimuli otherwise the same? We should expect that there's specifically a reduction in predictability at that level for that feature and not for the other features. So that was a test with this inverted condition here, because you can imagine, I mean, you're not familiar to looking at action inverted, so it looks really weird, and you can't really have this high level view invariant representation of body posture and motion, not as well, especially not predicted. This is also shown in other studies that don't look at prediction, but they just look at processing, and they'll show that it's much harder to process this and have a representation of this view invariant representation. Okay, so let's look at the results. So first of all, maybe one more thing. So we had now more subjects, so 43, we used 40 subjects in the end, but we have less data because we have 3 conditions now. So there's the amount of trials per video per condition is only about 15. And that causes the signal to noise ratio to be lower, and it causes your RSA results to be just lower in terms of values, because you're correlating your model with a noisier neural signal. So your values get a bit lower, and you can't really solve that with adding more and more subjects. It just gets cleaner with the more subjects. So the values are a bit lower, but in general, for the normal condition, the effects are exactly the same as in the previous study. And then if we look at this inverted condition, we see exactly what we expected. So we see that this highest level representation, predictive representation is, well, it's not completely gone, but it's much highly reduced. And I still have to, I have to still statistically compare these two actually. So this is now just eyeballing. But I hope to convince you that it's, at least for now, it looks like it's highly reduced. And then another interesting thing is actually that you see that it's increased for view-dependent body motion, so a lower level representation, and it's not really reduced for the optical flow direction. So this might suggest or indicate that subjects are still able to watch these videos and make predictions at some level, and in this case at view dependent body posture, body motion, they can still process these stimuli and make predictions. So that's the level at which they have to make predictions to be able to do the task. But they're not helped by this higher level representation anymore. Yeah. And then you also see something interesting happening here, where you see all of a sudden this peak that is lagged here. I'll come back to that after showing the last condition. So if you look at piecewise scrambled condition, we don't see any predictive representations anymore, luckily. So that's what we, of course, wanted to check with this condition. So all the predictive representations are completely destroyed, and we still see the lagged representations. It looks a bit reduced and also sharper, but that's because of the model autocorrelation. And yeah, again, I can at the end show simulations if you're interested, but in the simulations you see exactly that the shape and even the amplitude of the height of the peak is caused by the autocorrelation. So it seems that they're still representing them to the same extent, but not predicting them anymore. And another very interesting thing that we actually didn't really, well, I guess we could have expected it, but we didn't really hypothesize it, but is that we found this very clear lagged representations now for body posture. And that actually is very much in line with this predictive coding theories, because they actually, the most strict version is actually that if you have a very clear prediction of something predictable, then the sensory input that comes in that can be completely explained by your prediction, then this sensory input is explained away and it doesn't need to be processed further after the stimulus. So that's what you would expect in these, especially in this highest condition, maybe also here, that you don't see that much real bottom-up lagged representations. But then if the stimulus is not predictable anymore or much harder to predict, then you expect these peaks on the right here, what we see for body posture. So this would then be, sensory input that is not explained by the prediction yet. And, some people call this prediction errors. So you have a prediction and then whatever doesn't match your prediction is a prediction error. But I wonder if you cannot make a prediction at all, can you still call it a prediction error, or is it just unpredicted information? So maybe that's a broader term, unpredicted information. I don't know. All right, and then that might also explain why we then see here a peak all of a sudden for this one. We're still not quite sure why this is then at the lowest level, and we would expect it actually at the highest level, maybe. So those are still questions that we have. But in general, you do see when it's harder to predict, you see no prediction or less prediction, and you see a stronger representation after the prediction.
But there's also disordering of the brain areas, like the view invariant body motion, right?
Yeah.
To be strongest predicted with V1 and not higher.
Yeah. So no, but so first of all, of course, we're still looking at MEG data, even if it's source reconstructed. So I'm not sure how strong we can make claims about the location, especially because, there's 6 ROIs, but they're quite close together. Not all of them, but like the first 4 are basically very close together. And then in general, the signal to noise ratio in V1 is going to be higher. So we don't know if we can really clearly compare them with each other. There are some effects that you would expect that we do see, like for example, this view invariant body posture here is clearly strongest in LOTC, which based on action observation literature is what you would expect. Whereas these lower level representations are much clearer in the earlier visual areas. But in terms of prediction, we don't actually know exactly what to expect, because it's an open question. Where would a prediction originate, or where do different parts of a prediction originate, and where will we then see the strongest predictive representation? And that's an open question. It would be interesting to answer, but I'm not sure if we can really clearly answer that with MEG. Good. Okay, then I'll have some time still. Yes. All right, so then I'll just go to the discussion and then some future ideas that I'm working on. So with this new approach, we can see when our brain is representing different features of the stimulus. And in this case, we find that when the stimuli are highly predictable, then we find mainly these predictive representations, and in some cases not a lagged representation. And these predictions, they match this hierarchy, which is what you would expect. And then reducing the stimulus familiarity also reduces the predictive peak specifically for the features for which you reduce the familiarity. And it increases then the unpredicted information after the stimulus. And of course, now I showed these ballet dancing videos, but in principle, you could use this for any dynamic stimulus, naturalistic, like soundscapes and music, sign language, but also for, of course, a moving dot. So we're actually now working on which you could argue we should have started with, but now we're using an experiment with a simple moving dot. And then we're actually manipulating different simple features of this, like how fast does it move? And does the speed of this dot then actually influence the location of the peak? Because it's not, we don't know, it's an open question what determines exactly this predictive latency, right? So does it depend on our brain or on the stimuli, and probably both. So that's what we're manipulating with this simple moving dots. And of course, you can use MEG, EEG, but also other signals. They just should have a high enough temporal resolution and also be like dynamic enough. Because of course, if they're moving only very slow, so I doubt that it would actually work with fMRI because it's way too sluggish, and then your neural RDM is going to be way too correlated over time. Right. Then I'll just not go through all of these, but maybe some future ideas. So we're working now on an open data set where subjects looking at a movie, because I talk about this high level conceptual representation of the view invariant body posture and motion, but that's of course still not very high level. So if you have a movie, then there's a narrative, and then based on this you can maybe make even higher level predictions. So it's a question if we can find those in MEG data. Well, actually now we're working on an ECOG data set. So far, not really much luck yet, but it's more because the data set is not ideal and the stimuli are not ideal. So we might have to actually record this data ourselves. But that's one thing that we're working on. Then I'm also interested in so this was just a raw, or I mean, it's, well, minimally processed MEG data, but then I'm interested in time frequency domain, because there's some literature that would suggest that bottom up processing representations should be reflected mainly in alpha and beta oscillations, including predictions. And then, sorry, did I say so? Top down, yeah. And then bottom up representations should be reflected in gamma oscillations, and then sensory input and detailed visual information. But recently there's been some discussion about this. Martin Vink's group, they published 2 papers, so it's not really clear if this is really the case. But this is something that I'm currently analyzing. So I'm, time frequency convolving these data and then running the same analysis on these different bands. And that's actually, maybe I can quickly go to the next slide, because this is also something that you have many, many options in, again, like with a lot of the types of analysis that we do. And it's really not clear what is the best approach here. So of course you can just filter the data in these different bands and then look at and then apply the analysis. But then you're still not looking at all the information, right? You're not looking at information that is not phase aligned. Whereas if you then look at the power of an oscillation, then you get a different kind of information from the signal. But then you can compute power across the whole band, or you can do it per frequency and then apply the analysis on these and average afterwards, or there's many options here. So I'm actually interested in discussing this with if somebody has experience, not just, I mean, I have experience with time frequency analysis, but also thinking about multivariate analysis and maybe RSA on time frequency analysis or some, yeah, it would be interesting to discuss all these different options. One thing is also, for example, to look at the phase, because there are some studies that show that the phase of alpha is important for perception. So you detect stimuli better at a certain phase of the alpha oscillation in visual cortex. And one study also shows that if you can predict the onset of a stimulus, then it seems that you can phase align the alpha oscillations, of course not consciously, but that you phase align the alpha oscillations to be ideal for this incoming stimulus. So if that's the case, we're now talking about prediction. It's both temporal prediction and what's going to happen prediction. So you can imagine, in theory, that you can, if you know that the Belay dancer is going to move this way, then in neurons that are processing that area of your visual field, that you can align the phase in such a way that you're optimal for processing the upcoming stimulus. So maybe in the phase of alpha oscillations, we can also see these predictive representations. But yeah, that's just something I'm working on now. All right. Then I think, yeah, I have some, I think I'll leave it at this. So yeah, I started this project with Moritz in Italy at GMAC. And then the first experiment was just 2 of us. And then I moved now to Donders, but I'm still actually working together with Moritz, or we are working together with Moritz. And now I'm working with Flores as well, who knows everything about prediction. So yeah, that's where I'm working now. And the first experiment is actually published with the method, where it's explained in detail, and also the code, everything is on GitHub. So it's not a toolbox yet, but you can. I hope I commented it well enough and explained everything well enough that it could already be useful. But I have a plan to generalize it a bit more, because I now use this specific dissimilarity measure for the neural and model RDMs, and this similarity measure to compare the two. But of course, it could be a modular toolbox where you can just pick your own favorite dissimilarity measure, your own favorite input, your neural signal, whatever it is, your stimuli, and then yeah, it could be a more general toolbox. So that's a plan for the future. Yeah, so that's it. Well, yeah, so if there...
Yeah, sorry. Thank you, Eamar. If there are any questions, then please...
Yep.
More of a theoretical question maybe, but so you found that if you mess up the possibility to make predictions, there's basically a heightening of what happens post-stimulus, right? So would you say that your data kind of are in support of like a heightening rather than a dampening of what is being predicted, or is this, does this come from your analysis and not the issue of whether predictions are heightened by prediction?
So yeah, it's a bit tricky. Yeah, most of those studies that talk about that, they actually don't really talk about timing at all, right? They only look at basically what happens after the stimulus. So to really compare it with those studies, I would have to have maybe different levels of how unpredictable it is, and then see how this lagged peak changes. And then if it would become lower, then you could maybe say that the prediction is less, that the post-stimulus representation is less veridical or less. But in this case, we could say that if you reduce the predictability, yeah, that then you get a much stronger representation after the stimulus. So it is in line with predictive coding theories, because they say that specifically.
Trying to look at kind of the predictions that relates to the post-stimulus representation, like
No, I haven't looked at that, but that's an interesting thing. It's also one of the other things that I wrote down here, that you can actually, yeah, it's not exactly, well, with this you could look at it. So the third point, so what you have, of course, an RDM in different areas, and then you can also compute RSA between these different areas with different latencies. And then you can, yeah, then you could also compare like predictive and lagged representations with each other in the same area. Yeah.
I have a question about the regions. So, pick some regions, sensible. But after you found which specific features of the movie led to predictive signals in the neural data, did you try searchlighting it and see where in the brain the prediction was starting or ending? Or?
Oh, yeah, sorry. So Freek asked that we first applied this approach to this ROIs, but then if you know that you get this predictive representation, so these peaks here, can you then also use this and do a searchlight on those peaks? And that's what we did with these, you see these little plots underneath it. So that's a searchlight analysis. So we did the same analysis, but only on the latency of the peak, and then across the whole cortical surface. So basically we separated the cortex in all different regions of the same size, and then applied this analysis. And I mean, that's in line with the findings that we already found on the ROI level. So there's not really something very clear or surprising that pops up, or that we see something frontally. No, and I don't know if that's okay. So this is thresholded, statistically thresholded. So it's, yeah, and there's some things going on in the front, but I didn't really dive in. So here there's actually something here, and this is also quite like frontal. Yeah. But I didn't really then decide to dive into the spatial effects. But
another question I have is very different. You have eye position there, but obviously people make predictive eye movements. They're going to look where they think the person is going to be in the next frame or the next few frames.
Yeah.
So how do you deal with that?
Yeah. So we have a eye position model. Based on the eye tracker, so there was eye tracker data was recorded, and we created an RDM based on the eye tracker data as well for each individual subject, and then we included this in this regression analysis. So in the last step of RSA, you include it in the regression. So when you then test one model, you also ignore the variance from the eye tracker data, and then we also tested the eye tracker data. So you see that there's, and it's actually interesting that it also seems to be real time. So when you know something is going to, well, actually, no, this is a bit hard to, because this is now related to the neural data. Yeah. So, but it is an interesting question also that coming to the fifth point here, that you can also use the eye tracker data as instead of your neural signal. So completely ignore the MEG data, use the eye tracker as your neural signal, and then see which of the models can explain your eye tracker data and with which latency. So that is a plan that I have. And actually my roommate in Italy, so part-time roommate, he works a lot on prediction in eye movements and pre-saccadic effects. And so this is something that we want to also work on.
It would be interesting to do it also, like you say, with the music stimuli or something, where eye movements maybe are not so important.
Yeah.
Changing the way you process the stimuli.
Yeah.
So it'd be cool to see how it generalizes to a different modality.
Yeah, exactly. Or pupil dilation, I thought about that might be interesting as well. Although that's, I'm not familiar with it that much, but it's a quite sluggish signal, pupil dilation. But that would be interesting if you see some predictive pupil dilation, if you know something important or interesting is coming up. Or, yeah. Yep.
There also maybe individuals can contribute to the result because your stimulus is dense like this, right? There's this time maybe people are known how to dance a lot or watch dance a lot, maybe have higher predictive.
Okay, so the question was individual differences could be interesting because, of course, different people have a different level of familiarity with these stimuli. And yeah, that's interesting. So in this case, they're all naive observers. So they're not ballet dancers, let's say. And also these videos we choreographed, so they're not well-known, you know, ballet dancing sequences. So in that sense, people were not, in this case, able to predict like what's the next move or figure of the ballet sequence going to be. So they had to make the predictions based on a bit lower level information. But it is an interesting thing that we thought about, like comparing, actually having a well-known ballet sequence and then comparing novices and experienced observers, and then see if maybe the experienced observers, well, that's a question. Like before, we could already test whether they have a better prediction or not, but now we can also test whether the timing changes. And you might expect that they make earlier predictions. Yeah. Yep. The question was, can you already look at this familiarity effect by comparing, especially for the inverted condition, because that's new for them, for the subjects, compare like the first half of the experiment with the last half, because throughout the experiment, they might get more familiar with the stimuli. So we actually did that for the first experiment originally, because we also thought maybe that's the case there. We didn't see an effect, but I think that's because what I said before, like people are already very familiar with actions in general, with motion, like they know biomechanical constraints, right? You know that the arm can't move beyond like the elbow joint, what it allows you to do. When she jumps, the ballet dancer, you're familiar with how fast she will go back down to the ground. So all those things don't change within one experimental session. I mean, that's why I don't think we saw a difference. But you're right that the inverted condition is actually ideal for testing that, because in that case, people are they do get a bit more familiar with it. But yeah, I don't know if we have. I can do that. Yeah.
Right. Thank you very much, Ingo.
Thanks.